So now I want to give some nice applications of these kinds of cardinality arguments. So you may remember when we were talking about existence proofs, I mentioned an example of a non-constructive existence proof where you show that something exists without giving an example of it. And I mentioned, without giving a proof, the example that I will give you now. So a real number is transcendental if it is not the solution of any polynomial with integer coefficients. And let me emphasize that we're considering integer coefficients. For example, if you allow real coefficients, then every real number is a solution to a polynomial. But if you restrict yourself to integer coefficients, then not everything is a root. And this is some measure of how far from being an integer you are. So irrational numbers are a little bit farther from being an integer, but transcendental numbers are as far as you can get from being an integer, because they are not a solution to any polynomial with integer coefficients. So essentially they have nothing to do with integers. And the point is that it's really difficult, maybe I won't write this down, but it's really difficult to prove that a specific number is transcendental. So for example, the number e, the base of the natural logarithm, was proven to be transcendental in 1873. And for context, I mean, math is, an old and proud subject. People were doing calculus in the 1600s. It took 200 more years to prove that E is transcendental. And there are still, pi is another transcendental number. Pi to the power E is unknown, whether that is transcendental or not. That is an open question. So for a specific number, it's extremely difficult to prove whether it's transcendental or not. But we can make the following argument to show that there exists a transcendental number using just what we've developed today. So claim. There exists a transcendental number. Proof. Well, we're going to make a cardinality argument. So it's going to go something like this. I'll give you the rough outline. So we saw that the integers are countable. We saw that, so let's write down some unions of some sets. So consider polynomials of degree n so this looks like some coefficient times x to the n plus some coefficient times x to the n minus 1 plus some constant coefficient. So it's essentially just a list of n plus 1 integers. As the coefficients, I mean. So we can put this in bijection with n plus 1 copies of the integers. And I didn't prove this to you, but I hope I have convinced you, or at least said it enough times that you believe it by now, that if you take a bunch of copies, a finite number of copies of the integers, this is again countable. And now if we take all polynomials, well, okay, let me say with integer coefficients, very important. If we take all polynomials with integer coefficients, this is the union, maybe is there a different name, of polynomials of degree n with integer coefficients. And as we saw, a countable union of countable sets is again countable. And each polynomial has finitely many solutions. So if we take the set of all solutions of polynomials with integer coefficients, oh, my handwriting, excuse me. This is essentially a countable union of finite sets, because we're taking the union of the solution set of each polynomial, of which there are countably many. So this is also countable. And the complement of this in the real numbers is the transcendental numbers. So the real numbers equals this set union transcendental numbers. And as we have seen, this thing is uncountable, and this thing is countable, and that implies that this must be uncountable. Because if you had countable union countable, you would get something countable. So in fact, I mean, we've proven what we set out to prove. There exists a transcendental number. In fact, there are uncountably many transcendental numbers. So it's quite an amazing fact that somehow this set of transcendental numbers is a bigger infinity than this set of numbers that are solutions to some integer polynomial. So what this is saying is somehow, if you were to choose a real number at random, there is 100% chance that it'll be transcendental. I mean, if you choose a random real number, you are almost guaranteed to get a transcendental number. And yet, it's extremely hard to write down examples. So this is an example of the strange way that mathematics can work sometimes, that the way we have of writing these numbers down and working with them means that we are blind to a huge amount of what is going on. The reason that it's so easy to write down rational numbers is because there's something very, very special about them. And as a result, there's not very many of them. Whereas the numbers that are really out there, the more general sorts of numbers, we don't have any good way of writing them down. So we're kind of blind to them, even though they're absolutely everywhere. So let's do another quick example along the same lines, but with a more computer science / logic kind of feel. A function from the natural numbers to the natural numbers, positive integers, whatever you want to take, is computable if you could write down a program to compute its values. And by this I mean in theory. Not necessarily you know the algorithm, not necessarily like it's written down somewhere, but in theory there is an algorithm that computes the values of this function. So for example, some things that are obviously computable are, f of n equals n plus 1. We know how to add 1 to a number. This is computable. Any kind of arithmetic is going to be computable. But just to give an example of something that is not quite as obvious how you would write down an algorithm, if you take some function, for example, that spits out 1 if n is a prime number, and 0 if it's not, then you may not have an idea immediately in your head to write down this algorithm, but you can believe that there is an algorithm for determining whether a number is prime, and therefore you can write down an algorithm that produces the outputs of these functions, of this function. So, are there functions that are not computable? So maybe you see where this is going. We can use cardinality arguments to show that there are lots and lots of functions that are not computable. So let me be more brief about this without going into the details. But so programs, which we are assuming have finite length. So I was saying that implicitly before, but when I say there's a program that lists its values, the program is a finite list of instructions. No infinite programs. I don't quite even know what that means. Maybe you can make sense of what that means, but that's not what we're talking about. So programs of finite length essentially is a finite string of characters. I mean, however you decide to formalize what a program is, which you might want to do if you're being rigorous, but essentially it should turn out to be a finite string of characters from a finite alphabet. This thing is going to be countable. On the other hand, functions from the natural numbers to the natural numbers, how can we think about this set? Well, here is something we can compare it to. If we think about functions from the natural numbers to the set 0, 1, we can agree that this is no bigger than that, right? There are certainly more functions from n to n than there are functions from n to this finite set. And this we can put in bijection with a power set of n using a similar idea where f corresponds to a subset S and this correspondence is given by the rule f of n is 1 if n is in the subset, and 0 if n is not in the subset. So this thing, and therefore we conclude this thing, is uncountable. Because remember, we saw that the power set of the positive integers, which is very much like the power set of the natural numbers, is uncountable. So we conclude in fact, almost all functions are uncomputable. Although again, it may not be completely obvious how to write down an example. But if you're curious, this is another fun thing that there are some interesting examples of uncomputable functions that people have written down. So that is a good thing to go look into if you're interested.